I mean,
Yeah, it starts like.
I say that, but I totally do. I just am very focused. I do driving sims, I'm driving sim right now, and I have a cyclist. It's like cycling sim. Full time. So that technically is a game.
I'm gonna check.
Does it feel like a game to me? Because it's not much of an FPS, because those games I like FPS.
Well, I'm gonna do first.
So hi all again. Hope you had a good lunch. We're now resuming with our events for today, talks for today. So now Rabimba is with us and he's gonna talk about his work on DeepSpeech and how they got to a less than 10% error rate with this speech-to-text engine. So over to you.
Thank you, Ann. Hi, everyone. Good evening, good afternoon. Hope you all had a good lunch and feeling pretty sleepy. I'm going to make you more sleepy, or hopefully not. Let's see. Hi, today I'm here to talk about DeepSpeech, which doesn't exist in this form anymore. It exists in a different form, which we are also going to talk about. We are going to talk about a lot of things about speech technology, how voice to text work, how speech to text work, what are the problems, go a little bit into math, and then go about into the more interesting stuff of how you can use it, how you can train in your own language, and some more things. So before we start, what is voice technology? How many of you have, in some way or other, have interacted with any kind of speech-to-text technology? Awesome. I should have expected all the hands. So those who has not raised your hand, you have never talked with Siri or Alexa or Google Assistant or to your car? So all those are examples of voice technologies. They all use speech-to-text to convert your speech to a text. Before we go forward, because this will be interesting, is anyone here who speaks more than one language? Nice. Have you found a good speech-to-text solution for your own language? I didn't. So I speak something, so I'm from India, and I speak a language called Bengali, and I also speak a language called Hindi. When I look at my languages, I realize that there is no good speech-to-text available. And don't we want to have something where I can speak in my native language and it still converts it? Today, I'm going to show you how you can do it in your own language, how you can use transfer learning to actually use an existing model of speech-to-text and even get some amount of speech-to-text of your language going. If you have a community which contributes more data, you can have a good language built and contribute to the open source model as well. So going back to the slide, what is voice technology? If you see the robot, that's kind of like what we aim to be. So you are speaking with somebody, a tablet or something. So it's easier to work with text than speech. Machines had hard time understanding audio. So when we say audio, what they interpret is different like zeros and ones, but mostly a spectrogram like a wave. It's much easier to work on that. Instead of that, if you have a specific text, already libraries, we have plethora of work available on natural language recognition, natural language understanding, and natural language processing. So it's easier to work on text. With that in mind, when you see at that, the NL proc, that part, I will say that the natural language processing, that's the brains. To get to there, we have to have two things. First, we have to take our speech, convert it to text, that goes to the robot. And then the robot, if there is a secondary like bidirectional input to you, then we should have something where the robot should be able to speak, also text to speech. Even though that's not part of today's talk, I will at least tell you that how you can do that using the same language. Going forward, I hope this is legible. What we are going to talk about today, mostly this is the outline of the talk. I'm going to talk about a little bit about DeepSpeech, the library Mozilla built, how the architecture works, why some of the decisions were made for specific model, how the language learning works, very little bit about the mathematical models, like why those were chosen, and then go a little bit forward about the future research problems, a little bit of demo, and also how you can use it today if you want to use it in your own application. That's a little bit about me. Those are my friends. That's I wore different hats. Some of that in Mozilla, some in IBM. But see, my friends are cute. So let's dive in to the core architecture. So DeepSpeech started as a Baidu paper, then a Google paper, and then Mozilla started picking up from that Baidu paper and started implementing it in a very different way. And we're going to talk about the core architecture, what DeepSpeech is and what is there. So first, the architecture. So this, what you see in the slide, this is the core architecture of DeepSpeech. Basically, it takes some input features, and then after that, we have 3 feed-forward layers and a little bit bidirectional recurrent neural network layer. We have another feed layer and a softmax layer along with the CTC layer on top of that I'm going to talk separately. So this is our input feature. When I go into that input feature, so I'm going to not go into the maths part too much, but let it to you like what you will need. So imagine if you want to take an audio, for example, this speech, like this talk I'm giving it, there are a couple of ways you can input your audio to this DeepSpeech. First, if you see any documentation, you will see that they will tell you that you have to chunk the audio and you have to feed it. You can do a continuous audio, but if you chunk the audio, that has a better performance. Also, your audio has to be 16-bit mono audio. Why? This slide provides you the reason for why. So here we have an input speech. It's a 16-bit audio at 16 kilohertz. Anything other than that is not ideal for the architecture. How it works is that we take a little window, rolling window of 25 milliseconds each, and this rolling window moves after every 10 millisecond take. So the model actually runs in those. So another sample is to me that I can take another sample of these audio and take 25 milliseconds and create 26 of these celestial coefficients. And we also use a stride of 2, which essentially means after every 2 of these, we skip one of these windows. That makes it much faster. And we have also seen that that gives us a similar performance for that. We're not going to go to the architecture, but this is the reason behind whenever you try to use it, whenever you see that, okay, you should chunk your audios, you should have it in 16 kilohertz. This is the architecture, and this is why they're told. Going to the feed-forward layers. So in terms of these 3 layers, it's a really simple 3 or 4 layers width. Each of these layers has a width of 2048 bits, and they actually redo the cells. Once we have this feed-forward layers, it just takes the original audio and it passes through that. The bidirectional layer actually takes these, and we have, I can read the slide. Anyway, we have, we actually train these based on like a 248 layer widths, and this passes through that layer. The feed-forward layer takes on top of that and trains more on that. So if you have trained that, the reason for this is that can we give this layer a second chance? So this feed-forward layer takes whatever we have predicted and works on top of that. And then we have the softmax layer, and I didn't have the CTC layer slide. So what this layer and CTC does is that essentially it does the alignment correction in CTC. So when I am saying a sentence, and when you have your data corpora present, what happens is that you have your transcription, you have a sentence in text, you also have an audio along with that. Now, I can say a sentence very fast. I can say the same sentence pretty slow. So this alignment correction happens in the CTC layer. So going to the language model, this is what essentially happens for the loss function. I'm not going to the loss function explicitly here, because there were 3 versions of the loss function. I'll show that slide. That's in the backup slide. So essentially, we fixed in this loss function so that this provides us best performance for only English audio, and you can move forward with if you have a different language. So we are going to see a demo of how you can use this in a different language, and then I can show you that what parametric tunings you need to do. So what about performance? How good or bad this is? So this is kind of the performance you get out of it. What do these mean? Any of you have worked in speech technology before? So when you have something like WER, so what that essentially means is word error rate. How that's calculated is we have a golden data set where we already know that from a human transcription or something, that okay, this transcription already has these many words which are correct and these many words which are not correct. And we also calculate how many words are getting missed. When you pass that through any kind of speech-to-text algorithms, be that DeepSpeech, be that Meta's algorithm, Meta's Google's algorithm, when you pass them through, we calculate the word error rate based on how many words are wrong or how many words have been missed. And based on that, we can calculate that, okay, is it performing good or bad? So what we have seen is that our word performance rate has become pretty good, 8.48%. So that means anything less than 10% is supposed to be in the range of human errors. This, however, take this number with a grain of salt, because almost most of the research work, they are based on specific audiobook data. For most of the academic research, that's a data source called DeepSpeech. So DeepSpeech is a data set where people have audiobooks read by professional readers, and most of these algorithms actually run through that to give their kind of baseline output that, okay, this is performing well or bad. When you are going to implement it, it's not going to be same. Your audio might have noise behind it. Your audio might have a speaker like me who has a pretty different accent from your training data set. So we need to account for that. Before that, let's talk about what future holds for us. So we can change the network variants of it. We can change the different CTC layers, the RNN layers, and the convolution layers, which is not present at this moment. And then how about the data? All this is good and fine enough, but how will you build your own language model? How will you even use it if you don't have a data set? So coming to Open Speech Corpora, so these are kind of the data sets this has been trained. So Open Speech Corpora is available part of LibriVox and VoxForge. This has a specific data set. You can use these. These are open source. You can use this to build your own model. Then Mozilla has built something called Project Common Voice. You can use Common Voice to come up with your own community. You can have GDSCs, you can have other people contribute your voice to this, and this is open to everybody. So you will see new papers coming up from every part of industry which cites Common Voice as their data source, because Common Voice is a platform where anybody just can go contribute their own language voice data, and anybody can use it because they are part of the open license. So how this mostly works is that you have a web page, you just go there, you record your voice, and you also read out specific things, so the transcription pairs are present, and these can be used for different purposes. There are options like you can have different set of volunteers who come and validate those speech, that are those correct or not, are those properly getting transcribed or not. So some of the future directions is that these can be changed. One of the big pushes right now is languages, because there has been plethora of work, and there has been work ongoing on improving the language models. But one of the prime barriers of it is getting those language data in it. For that, you need language data, so that's why Common Voice is there. Otherwise, there are Translators Without Borders who also contribute models in here. So a little bit of demo, this is how it works, and this is not interesting enough, so we will actually run it in Google Colab to see how it works right now. Before we go forward, let's take a step back and see what is the development life cycle of a voice. So till now, everything I've talked about, that's regarding the architecture and the meat of it. But I want to know, if I am developer, if I want to build a voice application, and I don't want to know about how these things are built. I have already these as libraries. I will just want to pip install. I just want to use it in my application. What are the good practices? How do I go about it? So if you see this diagram, this is how a life cycle of a voice application works. So you have model training, you have model QA, deployment, and everything else. The whole thing starts with your data collection. How do you collect your data? Does it have a continuous feedback loop? How do your data gets annotated? So for most of the developers who start on any of these, they already have a data model, they already have a model for specific language that they are gonna use. Once they're gonna use, then they're coming to a very interesting part, is that how do you do a quality assurance on these applications? How do you do a data QA on that? That part gets handled. That parts get handled in a very innovative way, because how do you do QA on a transcribed language? So you have to have specific native language speakers who can say that, okay, your data is performing as it should, or in an unpredictable way, because it's machine learning. Then you have to have a proper way to actually get new data in, so that your model performs as intended. Most of your audience is not going to be the same speakers how your initial inference model is. So you have to have a way to monitor them and training that. We don't have everything else, so we don't have a same shoe fit for all models. So you need to have a model so that it is catered to your own audience. So moving to Kokui, what is a Kokui? So Kokui is a frog, but the reason I'm talking about it is today is once DeepSpeech model was developed, it went to version 0.9, then that team got dissolved from Mozilla. Now they're part of a separate open source organization called Kokui, that they're also a startup, but the same DeepSpeech code resides in Kokui. You can use it. It's under MPL license, so it's a commercial friendly license, so anybody can use it. And the same models which was being deployed in DeepSpeech right now gets deployed. It's the same code base, it just got renamed so that it can go out. I'm literally just going to show one slide regarding this, so you know what their websites are, how to contact that. So this is kind of their pitch, that they're developer-friendly speech solution. So they have a very good way to hack on those platforms, how you can build on top of that, how you can integrate your own language into that, so that you can actually keep building on that. Before we go to the pitfalls, let's actually see how you can. Let me just. Okay. Like that. Okay. So this is just an example of inference. If I want to do a very simple transcription on Kokui, and how you can do that.
So make sure it's streaming the right screen. You can select the entire screen. You can hide that.
So if you want to play with it, if you want to build that right now, I'll share this link, of course. But there are already like a lot of examples they have. So what you literally have to do is do a pip install. Here I wanted to get the really new one, so I did a wget. But you can literally do something like this, and it will install the HTTP client in your machine. So going forward, if I run it, I'm just going to run the whole thing and just going to go through with you. So literally what we're doing is just downloading their whole binaries, doing nothing else. And I'm going to get some audio files. This is an audio file I'm getting. And then I literally get a recognition model. So this is what we are using right now. This is an English large vocabulary model. There are other language models which we are going to see if it works, how we can do it. We're getting libsocks for processing that. And this is where you are getting your speech-to-text client built. And this is just from the same source code we just did. Once we ran it, this is running the tool, and yeah, so this is the transcription. So essentially, if you want to play with it, you can literally just do a pip install, and then you can literally, so you should download this model. This model, there's a model zoo from where you can download your specific language model. I just did it for English. So you just download your English language model. It's a TensorFlow Lite model. So you just download the model. You have an option to add a scorer, but that's an optional. You don't need it. Once you download the model, you just point it to your audio and you will get your transcription. So all those things I talked about, that how you like feed it to specific chunks of audio, the specific mono audio and everything, that gets handled. This audio is already mono, so this doesn't have to be, like, you don't have to do anything. But the SOX library we used here, you can use this to read the audio, or you can use a FFmpeg to actually change it to the required format, or even chunk it out and do that. Now, if I want to build this for a different language, so this is how you can do a transfer learning on an existing language model. So, for example, if I want to do it in a Bengali, what would I do? This is for Russian. I thought that would be more interesting. So this is literally, I'm getting a pre-trained English model, the same vocabulary model we used, and we download the Russian data language, the small data set we have, the transcription language, and then can fine-tune the English model using the Russian language, and then see how it performs. So when I run it, what it is doing. So first, the same thing, we are going to install the training data set. And if you want to do it, literally what you have to do, these are all pip installs. You don't have to clone it, you don't have to make it, you can do it, but you don't have to, unless you want to like live on the bleeding edge. Then we are gonna get the pre-trained English model. So that's literally from here, this model zoo. So we are just, no, not in my machine, but anyway. So from here, you could just download that. And then once we have it, we can download the Russian data models. This is this WAV file, this CSV, this alphabet. This literally is your different data, that you have a voice and you have the paired up transcriptions, and the alphabet is your language model alphabets. Once you have it, this is all you need to do the training. So we are getting using the checkpoint data that is already available in the existing model, and we are just pointing it to the training files, this Russian files and the alphabets. Once it runs, here we are actually going to use the training part. Once this is done, this should be done in reasonable amount of time. Probably should have run this before the other thing. I assure you, this didn't take this much time today morning, but live demos always fail. Yeah, it finished. In 45 seconds, that's not bad. Okay, so this is what we got. So I just ran a like test set from here. So we have existing testing data set which we can run to literally see how good or bad it performs using the same word that I told you about. So this is what we got. This is not good, not bad. Like when the word it looks pathetic. But anyway, so if you look at the loss and everything, but the point is, I just used a very small data set. I just ran something out of it. It was able to give me something. I don't know Russian, so I don't know how good or bad this is. Probably bad because this was the source and this is the result. You will see there are words missing, but you will also see it got a lot of them right. So this, more or less, maybe not more or less, but anyway. So this is how you can actually train it your own language. And I just did it in a Google Colab, no fancy thing, nothing, and just use it a very small data set within 43 seconds. So if you know a second language, if you are interested about it, you probably want to try it and just give it a go, see how good or bad it performs. And if you have a good community who is interested in donating their voice data to Common Voice or even to your own purposes, you can actually train that. Once you're done training that, what you're going to do with it? I mean, you can, of course, keep it to yourself, but I would suggest contribute it here. This is the models view. Here you have existing trained languages for every other, not every language, a lot of language. So for example, when I didn't find anything in Bengali, if I try to find something, there is a Bengali STT. Contributed by Alp. Alp is part of Translators Without Borders. So, and how he did it, this can be like completely separate demo altogether because Bengali has literally very less amount of voice data. So Google has an open speech data from Bengali. So he used that to train. Now comes the interesting part. This one, even though this is Bengali, it will fail pretty bad in my language, like when I'm gonna speak. The reason is, Bengali has, phonetically, it has two language codes. So whenever we talk about English, it's EN, and the language code. Bengali, it is BN-IN and BN-BB. So Bengali is spoken in two countries, in India and also in Bangladesh, and we have very different dialects and pronunciations and also words. Most of the data which comes to the open source speech corpora from Google, that's donated from volunteers from Bangladesh community. So that doesn't perform that well to mine. So what can I do? How Alp actually did it is that he took that, he did the same transfer learning I just showed to you in a bigger scale, and he was able to do the training in 24 hours. Now, if I have enough volunteers from the similar locality I am from, I can actually improve on the same data set to have it recognize our dialects and pronunciations better. This applies to your audience as well. Whenever you're going to build your own voice solution, it's not one shoe-fit-all solution. The same English, the same thing we just did here, and it worked perfectly well on this audio. This will probably not work well at all in my case. So when you're going to build that solution, you have to keep that in mind. And what is my... With that, we are almost at the end, and the common pitfalls you probably generally face. Don't assume a common size fits all purpose, because the same English we saw, if you put somebody from Scotland, from Wales even, it's gonna fail pretty miserably on that. Know your models. So your data is as good as, your transcription is as good as your data. For example, you are doing something for a new language or something else, and you have volunteers who are from age 40 to 50 and only males. In that case, there is a very good chance that the portal might not perform that well for females of maybe 20 to 30 or even less or whatever. So know your audience, know your data, and keep on working on that so that it doesn't get lopsided. So when you're working on any industry solutions, voice technology must be part of your whole life cycle. It has to be an iterative, creative process. It doesn't have to be just I have a model, I'm just running all through it. You should have a process of online learning where the transcriptions you are getting, where the transcriptions suggestions you are getting should be always iterative, and that feedback loops back to your project. Case in mind, there is a company called Fireflies AI which builds voice transcriptions for your meeting notes. They have a way of how your customers' feedbacks loop back into their model, and most of the companies do that. In natural language processing and voice teams must work together, because a lot of the challenges I told you about the data collection and everything NLP teams can alleviate some of your problems. They can do clever tricks to actually like make your life much easier. So you probably should work with them, not like work in silos. Also know your data. This is the really hard part, but you really have to have a way of listening to your data. This is not scalable at all. But when you are working with small language models or minority language models or really niche language models, you have to actually have a human in loop, actually listen to the transcriptions and see that, okay, where it's going wrong, which words is going wrong, is there a way to actually incorporate that specifically even word-wise in your model? And what are you measuring? Are you measuring your model properly? Like I said, word error rate is one of the like industry standards, but how it is done in industry is literally compare it to an audiobook that has a very specific speaker base who speaks in a very professional way in a noise-free environment. That probably is not your audience who is working maybe from a Zoom call or has a dog barking in the background. So you have to measure your own data, not from just like audiobooks. Define your use case. So see how your model works, see what kind of data you need to work on. If you have a studio environment, you are getting really good quality data. Do you want to downgrade that data to work on a model which was trained in a different way? So why not upgrade your model to use that data? Remember, when you are working with a team, every part of it is part of that team. So if your text model breaks, your NLP also breaks because it is getting wrong data. If your text model is working fine, then the NLP team is getting good quality data, and they, whatever inference they're making, whatever logic they're putting into it, that has more value instead of, so it's like literally garbage in, garbage out. With that, I would like to open up for question. If you have any question, I would be happy to take it. Thank you. So that was mostly to kind of give it a second chance to guess the words, because when we used it for the first time, it wasn't performant enough for all kind of audios. So we used multiple datasets, including an closed source dataset for the initial training part, and we realized it works very well for all of those datasets. The moment we go outside, like our own engineers, they fail. So we try to see, try with the concept that how can we give the guest like a second chance of guessing those words. So the same part, do it forward. So that was the main reason. This architecture has changed right now a little bit in Kokui. This was the original DeepSpeech architecture prior to 0.9. Now it is changed, it's way more performant, but yeah, that the main basics still remains same. Yeah.
Are there any plans to extend it to non-alphabetic languages, where like Chinese, for example, where like one sound doesn't equal one character?
It is, and I know we have Chinese traditional language models. I never put it inside the talk because that model itself is closed source. So like I cannot show you even if it works. And second is that is like a there is work going on, but that architecture is different from this. So it's a little bit going in a different way. But yeah, there is work going on in that. And I think I can point you to a demo which works in that. You will be able to run it. You will be able to get the model to run it your own, just that you will not get the source of those models. Anybody else? Thank you. Thank you. So that's me after every talk.